Put your hand on a block of ice. Feel that chill? Your brain tells you the ice is pushing cold into your skin. But here's the thing, cold doesn't actually exist. There is no such thing as coldness. What you're actually feeling is heat leaving your body. Cold is just a word we invented to describe less heat. And that raises a really interesting question. If cold is just less heat, and heat is just energy, then what happens if you remove all the energy? Every last bit of it? Is there a point where things literally can't get any colder? Turns out, there is. And the story of how we found it is one of the strangest in all of physics. To understand the coldest possible temperature, you first need to understand what temperature actually is. Imagine zooming in on a glass of water, past the surface, past the tiny droplets, all the way down to the individual molecules. They're vibrating, shaking, bouncing off each other in every direction. That motion is what temperature measures. The faster the molecules move, the hotter something feels. The slower they move, the colder it gets. So temperature isn't really about hot and cold, it's a speedometer for atoms. And that immediately raises a question. What happens when the speedometer hits zero? When every atom in the universe stops moving completely? Scientists in the 1800s started wondering exactly that. If heat is just molecular motion, then there must be a lowest possible temperature. A point where molecules have absolutely no kinetic energy left. No vibration, no bouncing, no spinning, nothing. A complete, total, utter standstill. Think about it like a car. A car can go faster and faster without any real limit, but it can only slow down so much. At some point, the speedometer hits zero and the car is just stopped. Temperature works the same way. There should be a bottom, and finding that bottom took a genius. In the 1840s, a Scottish physicist named William Thomson, later known as Lord Kelvin, did something brilliant. He studied how gases behave when they cool down. He noticed that every time you cool a gas by 1 degree, its volume shrinks by the same fraction, about 1/273rd of its total. So he ran the math forward. If you kept cooling and cooling, at what temperature would the gas shrink to nothing? The answer, negative 273.15 degrees Celsius. That's 459.67 degrees below 0 Fahrenheit. He called this the absolute zero of temperature, the point where molecular motion ceases entirely, the coldest anything could ever possibly be. Kelvin thought this temperature was so important that he built an entire scale around it. Instead of starting from the freezing point of water like Celsius, or some arbitrary measurement like Fahrenheit, the Kelvin scale starts at absolute zero itself. 0 Kelvin equals negative 273.15 Celsius. Water freezes at 273 Kelvin. Your body temperature is about 310, and the beauty of this scale is simple. There are no negative numbers, because you literally cannot go below nothing. Now here's where things get wild. As scientists learned to cool materials closer and closer to absolute zero, they discovered that the universe does incredibly strange things at extreme cold. First, the obvious stuff. Cool any gas enough and it becomes a liquid. Cool it more and it becomes a solid. But some materials refuse to follow the rules. Helium, for instance, you can cool helium all the way down to just 4 degrees above absolute zero, and it does become a liquid. But no matter how much colder you make it, it never freezes. It just stays liquid. And then, at around 2 degrees Kelvin, it does something nobody expected, something that looks like it breaks the laws of physics. At 2.17 Kelvin, liquid helium becomes a superfluid. And superfluids are genuinely one of the weirdest things in the universe. Imagine a liquid with zero viscosity, absolutely no friction whatsoever. Pour it into a cup, and it will climb up the walls, over the rim, and drip down the outside all by itself. It flows through microscopic cracks that no normal liquid could pass through. It can even create a fountain that shoots upward in a thin stream, seemingly defying gravity. Why does this happen? Because at temperatures this close to absolute zero, helium atoms stop behaving like individual particles. They start acting as one giant quantum wave. The rules of the tiny atomic world start leaking into our world. But superfluids are just the beginning. Cool certain metals and ceramics to near absolute zero, and they become superconductors. That means they lose all electrical resistance. Completely. Send an electric current through a superconducting ring and it will flow forever. Not for a long time. Forever. No energy lost, no heat generated, nothing. And superconductors do something even more dramatic. They repel magnetic fields so strongly that a magnet placed above a superconductor will just hover there, floating in midair. No strings, no tricks, no power source, just pure quantum physics refusing to let the magnet fall. It looks like actual magic. Go even colder, down to just billionths of a degree above absolute zero, and you enter the realm of the Bose-Einstein condensate. This is a state of matter that Albert Einstein predicted back in 1924, but scientists couldn't actually create one until 1995. Here's what happens. At these unbelievably low temperatures, atoms slow down so much that their quantum waves start to overlap. The atoms lose their individuality. They merge together into one single superatom, behaving as a unified quantum object. It's as if a stadium full of people all suddenly started moving in perfect synchrony. Same speed, same direction, same rhythm. Individual identity, gone. This isn't a gas, liquid, or solid, it's something else entirely. So now the big question. If all these incredible things happen near absolute zero, what happens at absolute zero itself? Here's the frustrating truth. We will never know. Because the third law of thermodynamics says you cannot reach absolute zero. Ever. It's not a matter of building a better refrigerator or finding a cleverer technique. The laws of physics themselves forbid it. Absolute zero is like the speed of light, but in the other direction. Just as nothing with mass can ever reach the speed of light, nothing with temperature can ever reach 0 Kelvin. It's a boundary built into the fabric of reality. Here's why. To cool something down, you have to remove heat energy from it. At normal temperatures, that's relatively easy. A refrigerator does it all day long. But as you get colder and colder, each tiny step takes exponentially more effort. Think of it like this. Going from room temperature to minus 100 degrees, not too bad. Going from minus 200 to minus 250, much harder. Going from minus 273 to minus 273.1, almost impossibly hard. And going that last tiny fraction, it would take more energy than exists in the observable universe. Each step closer to zero requires double the effort of the step before. You can get infinitely close, but you can never arrive. But scientists are stubborn, and they've gotten astonishingly close. In 2003, researchers at the Massachusetts Institute of Technology cooled sodium atoms to just half a billionth of a degree above absolute zero. That's 0.5 nanokelvin. To put that in perspective, the temperature of outer space is about 2.7 Kelvin, warmed by the faint afterglow of the Big Bang. These lab experiments are billions of times colder than the vacuum of space. The coldest known spot in the entire universe is not on some frozen moon or in the void between galaxies. It's right here on Earth, inside a physicist's lab. That fact alone should blow your mind. You might wonder why anyone would bother getting this close to absolute zero. What's the point? Well, it turns out that the technology born from chasing absolute zero is everywhere. MRI machines that scan your body use superconducting magnets cooled to just a few degrees above absolute zero. Quantum computers, the kind that could revolutionize medicine and artificial intelligence, only work at temperatures near absolute zero. Even the discovery of the Higgs boson at the Large Hadron Collider depended on superconducting magnets kept at 1.9 Kelvin. The race to reach the bottom of the thermometer isn't just curiosity. It's driving some of the most important technology of our century. And there's something even deeper. By studying matter at extreme cold, we're peeling back the layers of reality itself. Quantum mechanics, the strange rules that govern atoms and particles, usually stays hidden at everyday temperatures. But near absolute zero, the quantum world becomes visible. Atoms become waves. Particles lose their identity. The boundary between individual things starts to dissolve. In a very real sense, chasing absolute zero is chasing the fundamental nature of existence. We're asking the deepest question there is. What does matter really look like when you strip away all the noise, all the vibration, all the chaos? So the next time you grab an ice cube or step outside on a winter day and think it's cold, remember this. Cold isn't a thing being added to you. It's energy being taken away. And at the very bottom of the temperature scale, where all atomic motion would stop, there's a floor that the universe itself refuses to let us reach. We can get tantalizingly close. We can cool atoms to billionths of a degree above it. But that final step, that last infinitesimal fraction, nature says no. There's a floor to the cold, and we can never quite touch it. If you like this video, check out one of these, and don't forget to subscribe.